Log on, tune in, find out. Another good idea from Cambridge.
I'm going to talk about statistical experimental design and climate ensembles, and I'll start off with a bit of a review of experimental design in this area, and then I'll go through some work I've been doing, and then I'll have some speculation towards the end. So, why ensembles? Well, I probably don't need to tell this audience this, but we don't just want a point estimate of what we think future climate might be. We'd like some uncertainty measured across that, and you need to do that with ensembles to do that. And if you want to calibrate models again, you need some measure of what the spread you're getting. And again, sensitivity analysis, if you want to know what's driving the model, what inputs actually drive the outputs, then you need to run ensembles. So I'll go through a little bit about designing experiments in general, and then I'll talk about computer experiments and climate models. I'll talk a little bit about optimal design, go through the designs, and finally I'll talk a bit about multi-model ensembles and draw some sort of conclusions. This is in a sense what first got me interested in designing computer experiments. This is a reconstruction by me. It's not the actual plot that someone put up on the board. We had a seminar at the National Oceanography Centre by someone who was running a computer model. It wasn't actually a climate model, it was a fluid dynamics model. And he had two parameters, and he started off by doing this point, and then he explored down here, and then he explored down here, and he found something interesting here, and he explored up here, but he really didn't have a design. He'd done one point after the other just where he felt was useful, and I think if he'd actually planned something out beforehand, he'd have done something much more efficient with his computer time, because he stopped here because he ran out of computer time, not because he solved the problem. So the point is, can you actually do better with a designed experiment? So we'll talk a little bit about experimental design, why we should be interested, say some space filling designs. So what is experimental design? Well, it developed from agricultural experiments in the 1920s, that big explosion of statistics at Rothamsted. And basically it was how you would apply how you would apply treatments to experimental plots in the field. And some of the times the terminology from agricultural experiments is taken into experimental design. So people will talk about treatments and plots even though they might mean climate models and different solar forcing or whatever. Experimental design owes an awful lot to R.A. Fisher, who's probably the greatest statistician of the 20th century. And he came up with ideas like randomization, block designs, Latin squares, split plots, and lots of other extremely complicated stuff. And he will reappear. The other great place of experimental design is clinical trials. And I'm sure everyone's heard about clinical trials. And again, randomization is really important. Blind and double-blind trials so that the people actually doing the experiments don't know what the treatment, whether they're applying a treatment or which treatment they're actually applying. And the idea of sequential designs, which again will come up later, where you modify the design as you go on. In clinical trials, if you find one of the drugs you're testing is actually killing people, then it's probably a bit unethical to carry on with your design to the end, so you modify it as you go through. So why should we worry about designing climate ensembles? Well, ask the rhetorical question here, would you take medication that hasn't been through a properly designed clinical trial? And you'd probably say no. So would you set climate policy which hasn't been through a properly designed ensemble? I'll leave it as a rhetorical question for the time being. Now, let's talk a bit about computer experiments, and I'll this talk's a bit interchangeable. Sometimes I talk about climate model ensembles, and sometimes I'll just talk about computer experiments, because the same ideas hold whether you're designing an experiment for an aero engine or you're designing a climate model ensemble. A lot of it carries across. So sometimes I'll talk about computer experiments, and sometimes I'll talk about climate model ensembles. They're the same thing. And they're actually very different from clinical trials or field experiments. So we need different designs to use them. Generally, we're trying to explore properties of some computer simulator over some parameter or input space. So mathematically, we can think about our computer simulator as y equals some function of some input. So this is our outputs. This might be temperature increase over the next century, and these would be inputs such as parameters, I don't know, ocean viscosity, that sort of thing. This is an unknown mathematical function which we can write down at certain places because we have this computer simulator that can tell us what's going on, and these things are often very high dimension. So normally we want to make some inference about the model or some inference about reality. So we need to estimate what the model does at inputs we haven't run it at to do those inferences. And sometimes we want to optimize the model parameters with respect to some data, or we might want to make predictions, which is generally in climate, that's the sort of thing we do. We might do this through an emulator, and we've had a number of talks last week about emulators, where we say that we're going to model our function, and I've now changed x for theta. So this is our climate simulator, and we'll say it's approximately equal to some statistical model, where this is a mean function, and this is a zero mean Gaussian process, and that just gives us a statistical interpolator of the model. And for the first part of the talk, you don't really have to worry about that, but the second part I will use this fact. So here's just an example of an emulator. There's a nice nonlinear function. In fact, I think that's sine x plus x. It's not a very complicated function, but it is very nonlinear. And we take those 4 points, and we take the data away, and we put an emulator through there. So I've only told the mathematics those 4 points. So we get a mean emulator, we get uncertainty around here. There's no uncertainty at these points because we know the answer. And then if I put the data back on, you can see we do a fairly good job. So emulators are just a way of statistically interpolating between the data points. So what's a good experimental design? Well, we want to make our inferences the highest accuracy with the minimum cost. The cost in this case is going to be computer time. We want to do the minimum number of runs to make accurate inferences. And there's a branch of experimental design called optimal design, and it comes to the idea of the thing called the Fisher information, which is Fisher popping up again, which is approximately the inverse of the variance of the output. And you want to maximize the information, which is the same as minimizing the variance, so we're trying to make everything as accurate as possible. And there are things called de-optimal designs where this is the matrix for high dimensional stuff. You minimize the determinant of the variance matrix or maximize the determinant of its inverse. And then there are also things called a-optimal designs where you minimize the trace. And there are, if you get into optimal experimental designs, there are I, V, G, and E optimal designs, and I can't remember what all of them are. I think E is you optimize the maximum eigenvalue of the variance matrix. Most people only talk about the optimal designs, and sometimes they talk about a-optimal designs, usually when they can't calculate this one. And if you want to be Bayesian, you can set up a de-optimal design by maximizing utility. So this is the variance matrix in some design, so this is the output given our design. You take the determinant, take log of that, multiply it by the prior, and just integrate over all values of your input. Okay? And we will come back to that. So this is usually, if you ask people to design an experiment, this is usually the first one they come up with. So I've got two, I'm going to do everything in 2D so I can show it on a board, but you've got to imagine this is actually happening in something like 40 dimensions. This is what's sometimes called a star design, or a one at a time design, and we vary parameter 1, and then we vary parameter 2, and we then try and make some inferences. The problem with this, I hope, is fairly obvious. You have nothing up here, and there's a wonderful quote from R.A. Fisher from 1926, which shows that, well, I think the first thing it shows that people use much flowerier language writing about science in 1926 than they do now. He also contradicted his boss, who'd written something the year before saying you should do one at a time. But if you only do the one at a time, you miss the possibility of the interactions. We know our climate models are highly nonlinear. Things are interacting. Star designs one at a time is not a good thing to do. So if we write down what we'd like our design to do, we would like to span the whole input space. We'd like to see all possible values. We'd like to observe these interactions, so we don't just want to be on the axes, we want to be out in space. And we'd like to minimize the number of model runs we do, because this is expensive. It could be incredibly expensive. So that brings us on to what are called space-filling designs, and they fit into, well, there's at least 3 classes. There probably are some others down here. But there are factorial designs, Latin hypercubes, and pseudo-random sequences, or nets, and the most important one here is the Sobol sequence. And I'll briefly describe each of these. The full factorial, where you set each input and factor, which again is one of these things that comes from the history of experiments, and you have all combinations. So if you've got n levels of m factors, you need n to the m points, and that gets big very quickly. Here's an example of a 5 squared factorial, which is not that big because we're only in 2 dimensions, but as you up the dimension, everything just explodes. This covers space quite effectively, but it is incredibly expensive. You can do fractional factorials where you only do some of those. You only do some of these points, you don't do all of them. They're really only being explored in 2 or 3, well, for large factors you really can only do 2 or 3 levels. Generally, fractional factorials have only been done for 2 levels up and down. And up and down really isn't enough for the sort of nonlinear behavior we're trying to catch. So factorials probably aren't good enough. So the next one is the Latin hypercube. To build it's easy to build Latin hypercubes to explain it, but let me explain what you do. You decide how many runs you can afford, and then you divide each input into that number of equal ranges. So we've got n runs, so we split input range into n intervals, and we allocate a point to each of those intervals, and then we shuffle them together across the dimensions. Okay, so there's the Latin hypercube in 2 dimensions with 3 points. So on each margin, each interval is covered, and I only have 3 points covering the whole space. Great, so we've now got an algorithm for generating a space-filling design. The problem is that this is also a Latin hypercube, and we probably don't like that one because it's got big holes. So we don't have an algorithm for the optimal Latin hypercube. Here's a rather more, so we don't have the algorithm for the optimal Latin hypercube. We don't have the de-optimal Latin hypercube. There are a number of ways to generate good Latin hypercubes. One's a thing called maximin, where you maximize the minimum distance between the points. So we generate 1,000 of these things, and we take the one that pushes points as far apart as possible, so it fills space a bit better. There are what's called orthogonal designs, where you say I'm interested in certain interactions and I want those interactions to be good, and then again we select Latin hypercubes with those properties, and then you can do pragmatic things and computer experiments or ensemble design. People often do very pragmatic designs. I'll talk a little bit more about that later. So there's a rather more serious Latin hypercube. That's a 25-point Latin hypercube. That's just one I generated. You can see in some places the points are quite close together. There are possibly some holes you'd be a little bit worried about. So that's a maxi-min Latin hypercube from 10,000 Latin hypercubes. They're incredibly quick to generate, so you can generate 10,000 a second and take the best. And you can see that it's now pushed the points further apart. You're getting a better space filling. There are still holes. There will always be holes, particularly when you get into high dimensions. High dimensional space is big. So one question you might ask, are factorials, which we know cover space very well, better than Latin hypercubes? If you can afford a factorial, should you do a factorial rather than Latin hypercube? The factorial guarantees you don't have any holes, though of course there are holes in between the points. But if you actually found there was no interaction between these two variables, so this one and this one were independent, in effect we'd only have 5 points here, because these would all be the same. Here we'd still have 25 points, so on the margins the Latin hypercube outperforms the factorial. So in many ways, even if you can afford the factorial, the Latin hypercube might be a better design. Okay, the alternative to Latin hypercubes are what are called low discrepancy sequences. These were developed in the 60s and 70s originally for pseudo Monte Carlo integration. If you want to do an integral over high dimensions, the most efficient thing is some form of Monte Carlo. These are designed to be even more efficient than Monte Carlo. And there are a number of things, the Holton sequences, needle-writer nets, Sobol sequences. For some reason in experimental design, everyone always uses Sobol sequences. I don't know why, but that's what I'll talk about. These are called low discrepancy designs, and you define this thing called the discrepancy, which is the largest you have. This is setting up little spaces. You build space up from little blocks, and then you count the number of blocks in each of these spaces, and you integrate over it, and you maximize the difference between the average number of points minus this integral over the space. So you're trying to maximize the number of points in space. That's what discrepancy is defined as, and it's believed but not proved that minimum discrepancy looks like this. This is the smallest one will be smaller than this value. So we're looking for small values of this thing CD here. And so there are various algorithms for doing this. And the one everyone uses is a thing called the Sobol sequence. I'm not going to define how you build a Sobol sequence. It's quite complicated. It's all to do with bits. And it can be done very efficiently in a computer because it's all done, say, with bits. So if you use bit arithmetic, you can actually very quickly generate them. There's quite a good description of it in numerical recipes. If you read it, well, whenever I read it, I understand it, and then 20 minutes later, I don't particularly understand it. But it's not necessary to understand it. You can just generate it very quickly. A 2 to the n minus 1 Sobol sequence has the Latin hypercube property of the marginal property. You get one in each element on the margins. Now, some projections of multidimensional Sobol sequence are not good in the points line up, and I'll show that in a minute. There is code to find those dimensions, and you can do things like allocating the inputs you're not interested to those dimensions, those projections that don't give you really good. that's what a Sobol sequence looks like. That's a 25-point Sobol sequence. You can see, unlike the Latin hypercube, this isn't random. There are symmetries in here. And if we go to the 31 point, which is one that's the Latin hypercube, you can see we've actually, the reason it's a Latin hypercube is we filled out all those symmetries. So you get this symmetry across there, and there's some symmetry across here. And it will now go in, it will start filling in the gaps here as we do the next 2 to the n points. You can improve Sobol sequences, removing some of these bad directions, by a thing called scrambling. And I have to admit, I don't fully understand scrambling, but it involves randomly permuting some of the binary digits in the sequence. It generates it. And if you do that properly, and there are 3 or 4 ways to do it, they're still Sobol sequences. And here is an example of one I generated this morning. This is a scrambled Sobol sequence. And you can see that the scrambling, by randomly permuting these things, we've pushed things away from this symmetry, so these bad directions don't tend to exist anymore. And that's the scrambled sequence. And there the little squares show the original Sobol sequence that it's been scrambled from. And you can see the points, each point has been just moved a distance away. Okay, so that's a sort of review of what people do to design computer experiments, climate ensembles, and last week we had 2 examples, one of which used Latin hypercube and one of which used a Sobol sequence. And I don't think there's any reason to prefer one over the other. Now, so far I've talked about one-off designs. We make a design and that we run it, but that doesn't allow us to learn from the early runs. Well, we could learn from our runs and then do extra runs that put that in a sort of sequential way. And one way to do that, we might perform an initial experiment, usually a space-filling one, and then add some points to satisfy some criterion. So we might add points where predictions of the similar output are most uncertain. We build an emulator, and where our emulator isn't very good, we'll run another point. We'll run another value just to see if we can knock down the uncertainty there. We might add some additional points for optimization. We might want to optimize something. We haven't quite got what the place we're interested in, so we'd add some extra points there. We might want to, if there's a discontinuity in our model, some process happens at some point, we want to find that point. Our emulator might predict where there's going to be a sharp gradient, and we put some points in at those points to actually generate, to find that step function. So sequential designs allow us to be pragmatic. They also allow us to do some other things, and I'll talk about one of those now, which is some work that I've been doing, and that's looking at a design for looking at the smoothness parameter of the emulator. And if we go back to the slide about the emulators, we have this Gaussian process, and there's a variance term which we can estimate, and there's this correlation function, and that correlation function has a smoothness parameter, a length scale, that is quite hard to estimate. Anyone who's ever fitted an emulator will know this, that the tricky bit is getting that smoothness. So can we actually have a design that helps us to do that? Well, pragmatically, you might think that if I want to estimate these smoothness parameters, I don't want to push the parts too far apart. If I push them all a long way apart, then I don't get a good estimate. If you think of the smoothness parameter, the correlation function is looking like that. If I only have data out here, it's very difficult to see what's happening here, which dictates the length scale, this length scale here. So intuitively, we would like a nice spread of parameters at different distances. So we might want something that looks a bit like this, a sort of harmonic function. And we can actually produce one of these Bayesian design utilities and actually estimate a d-optimal design. The reason we can't do that for space filling is we don't really have a measure of space filling that we can actually optimize. No one's yet come up with such a thing, and it would be very interesting to do so. But we can here, and you can show that for one of these Gaussian processes, the Fisher information is given approximately by this thing, which we can easily calculate. And if we do that, we can calculate this utility. And this shows the utility of taking a 5-point Sobel sequence. Where would I put the next point to maximize that utility to get the space filling design? And the redder it is, the better the utility. And before I did this, I expected I was going to get little roundels around all the points because it wanted to put one close to it. But of course it's more complicated than that because it's looking at all the distances to all the points. So you tend to get these ridges, and that the optimal one is somewhere around here. This is for a 10-point Sobel sequence, and things come probably a bit clearer in that we get this ridge. So I've swapped the color scale over, so now the whiter it is, the bigger the utility. So we're now saying we want points here, though there are some positions out here which are suboptimal but are still of interest. So if we actually take our 10-point Sobel sequence and then we add in the point, and then another point, they're actually all along this ridge in the middle, and they keep just filling in this ridge in the middle. And I think that is because it's the distance to all the points that matter. So being in the middle, if you try to put a point out here, this distance would be huge. It doesn't tell you anything about the correlation length. So you want points in the middle, and they need to be along this ridge because that gives you the short distances as well. So I think we can explain why we get that. That's taking one at a point. Oh. I think the slides got out of order. That's taking one point at a time. What if we actually take 5 points at a time? We might not want to just do one at a time. We might want to take 5 at a time. We might do our new runs in some parallel computing system where doing 5 at a time is more sensible or something. So this is the one at a time thing. I've added 5 points. If I add 5 at a time, I get this plot, which isn't quite the same. And that might be because my optimization, which I do here, is not perfect. If we overlay those, you can see that it does put points along that ridge, but it puts one point over here, for instance, and another one down here that are not normally there. The optimization is a sort of simulated annealing system, and it might be that it hasn't found an optimum, it's found a good value. Whether it matters that much as to which is actually the d-optimal design. If we flip back to this point. So the idea to take this forward into an actual operational design is you propose some new set of points to add to our system, and we'd actually not yet run the model. We'd emulate the function at those points, we'd emulate the climate, and then we'd rebuild the emulator assuming that our emulation gave us the right answer. And then we could use that emulator to estimate the integrated uncertainty and go back up here, do this system continually, sampling from the emulator to see which is the most efficient to actually add more points to our space filling design, or to actually try to estimate the space scales better. I haven't actually implemented that yet. Yeah. So that's one example of a sequential design for a particular purpose. Another thing we might want to look at is when we build an emulator, we want some diagnostics. Diagnostics used here in the statistical sense, not the climate modeler's sense. In the diagnostic is a test of the statistical model we're building. So we want some way of telling whether we've got a good emulator or not. Not all emulators are good. The sort of classic way to do this without doing any extra runs is what's called cross-validation, where you drop one out, you emulate that one, see how well you do, and continue doing it. The problem with cross-validation is that if you've got some optimal design and I keep dropping one out, I'm continually working with a non-optimal design. So it's not, there are some problems with cross-validation. So there's an interesting paper by Leo Bastos and Antonio Hagen where they propose some tests where you do a second run, and there are various tests you do by emulating the second set of points from the first set, and to do that, so you need a second experiment. And this is where I'm getting into the speculation. We want this second diagnostic experiment to cover space because you want to check the emulator is good everywhere, so we want a nice space filling design. But we also want to check that the emulator is good at all distances from the original points. We want to know that it's not, in particular you can get overconfident emulators where the uncertainty bounds are too narrow. And we want to test that even close to points we actually run. So we want to test all the distances. And so some good criteria for these diagnostic experiments would be they should be space filling, so that points us at maximum Latin hypercubes and several sequences. But we also want some distance criterion from this original experiment. We want it to have the distribution of distances from the original point should be approximately uniform, though you have to be a little bit careful here because if you're working in the unit cube, some distances are less, you can't get some distances, you get to long distances. And so we have these two criteria, and you could think that, well, I was talking a minute ago about estimating length scales. Well, those two criteria are actually quite good at estimating length scales themselves. So we might be able to build an experimental design that does both of these things, and it might actually outperform my sequential designs. I haven't actually built one of these yet, so this is all speculation. But it shows the sort of thinking you can do on some of these design issues. Okay, so far I've only talked about single simulators. I've only got one model and how would we design to look at uncertainty or sensitivity in one model. How might we design for multiple models? And you can think of this as the IPCC problem. They've got lots of groups around the world who are all building models and running them. And people usually call this the ensemble of opportunity. Last week I saw someone describe it as the ensemble of lost opportunity. Because they're not designed. The groups around the world put a lot of work building these models, and they generally run them at their best estimate. There is no coordination of what that best estimate is. I think it's hard to work out what the best estimate should be because the models have different inputs. So the input spaces are not comparable. There are common outputs, so we can actually locate them in output space, but we can't actually locate them in input space. If you have a traceable hierarchy, then yes, you can lock them into at least subspaces on the way up, so you can do some quite nice things there. But for multiple simulators with different outputs, I think different inputs, it's an important area for research, and it's one that I don't think anyone has any good ideas on. I don't have any good ideas on it. If anyone does, let me know. So I think that's a difficulty. Conclusions are that if you design your model ensembles rather than just running them one at a time, you can actually make the whole process much more efficient. And the other thing is, when you do the design, it actually makes you think about the problem more deeply. The process of design before you actually run anything can actually help in setting out what your problem is. There are a variety of designs around. They all have different properties, and my plea is, if you are designing a computer experiment of any sort, you should actually talk to someone, a statistician, about that before you do it, so you don't do things like star designs. Andre Soltelli from the Joint Research Centre in Isbra has a big long list of papers in Science and Nature that used star designs, which he fumes about at meetings. Design of computer experiments is an active area of research, but probably not so much in climate and environmental sciences as in the industrial area. So you might need to go out of your usual literature to find some of this stuff. It's a lot of it's come out of industrial design, where extra runs of the computer is real money, and they put a lot of effort into trying to get good design. And I'll stop there. Any questions?
So you're talking about these diagnostic runs after you do your big
Yeah.
experiment. Can you limit the number of runs because you don't want to do
Yes.
a huge number?
You don't need to do a huge. You don't need to do a huge number. You would do. You do some design with lots of points, and then you hold back some runs, and then you do those to test your emulator. Once you've sorted out you've got a good emulator, you fold those back in and you build an emulator using all of them. So the final emulator uses all your runs. You just hold some back to do these diagnostics, just to check you've got a good emulator. Okay? Yeah.
So I suppose you've been really talking about computing expectation values, generating appropriate ensembles, right? And in your case, I think you focus mostly on the unit interval, right? I mean, the unit cube.
Yeah.
So there must be, I mean, there are zillion scenarios you can think of, right? I mean, if you know that something is like Gaussian, for example, and how to distribute the points optimally.
Oh, okay.
And like you have some prior information about what,
yeah.
what PDF you set.
Generally, people do these designs on unit cubes, but you transform everything to the unit cube, and then you transform it back again afterwards. So the design is usually done on the unit hypercube.
But then you assume somehow uniform distribution.
Yeah. No, I'm not assuming a uniform distribution. You can, I'm not assuming any distribution. With the Latin hypercube, there is some discussion about whether, when you divide this up into intervals, those should be intervals in real space or in probability space, because you could make these equal probability.
Right.
And if you're sure you've got a Gaussian distribution,
well,
then you can do that, and then you get more points in the middle,
right,
and fewer in the tails, because you might be interested in the tails, because often we're interested in the rare behavior extremes, which means you might not want to do that. So there is a discussion of whether that's a good idea. I vacillate between the two. Sometimes I think that's a great idea, and sometimes I think, no, you must never do that. It's bad. So you need to think about it, about what the purpose of the experiment is. But yes, certainly with Latin hypercubes, there are two schools of thought. One divides it into equal probability, and one divides it into equal just value.
When you wrote the emulator description down,
Yeah.
you have to make certain assumptions about Gaussian distributions and so forth. But are there any assumptions there where are there any circumstances where you wouldn't want to make those assumptions?
Okay, the assumption, the Gaussian process thing is a bit misleading, because the Gaussian assumption we're making is the uncertainty is Gaussian about our curve.
Yeah,
Okay.
I'm going to ask you actually, could you?
Right, but you don't have to make that assumption. If you build what's called a Bayes linear emulator, You make no probability assumptions at all, but you only have a mean and a variance, so you can't make any probability statements. But the equations are absolutely the same. So you can do it and just say, well, I'm just going to have a mean and a variance, and then I don't have to make those assumptions. You are making an assumption about smoothness, in that this correlation function says that the point here is informative about the point here. So if you know something about this one, it tells you something about this one. And there are assumptions of stationarity built into that. You can get around some of those assumptions, but the smoothness one's different. If you have a function that does that, then knowing something here doesn't tell you about anything here, so you violated your smoothness assumption. In practice, you seem to be able to get away with that, and your emulator would have some sort of Gibbs phenomenon here and do something like that. And that's where you want to, with the sequential design, you start putting extra points in here to lock that down. So yes, there are positions where emulators, the assumptions of the emulator are violated. It seems usually you can get away with it. It's just fitting a smooth curve. If your model wasn't, if your model output looked like this, looked like random noise, then you couldn't fit an emulator to that. But would you actually want to run such a model?
What I'm curious about is things like situations where the mean and the variance aren't very, either don't exist or are very, very violently variable.
Yeah, well that's the sort of thing here, where your model output is very, very noisy. Yeah, okay, we'll talk about it. Yeah, you might want to emulate something else in that case, not necessarily the actual output. Yeah.
So for the PCC problem,
Yeah.
would you like to convince the community to design at least for the inputs that are shared amongst our models?
Yeah, I mean, if there are shared inputs, then yes, we could design across those shared inputs. My worry is that a lot of these shared inputs are inputs with the same name, but they may not necessarily be the same thing. It depends on the structure of the model, and you have to be quite careful, which is why if you have this traceable hierarchy, if you're using the same bits of the same code, then yes, there probably are things you can track across. I mean, I think we should do, if you want to, what we should do is each of the models should run its own little uncertainty experiment, and then we could start comparing the models on that. If we had an uncertainty map, the uncertainty modeling comparison experiment, where everyone did an experiment rather like the ones I've been talking about here, and then we compared the uncertainties across, I think that would get us somewhere. You've still got this problem, you don't know where in space you're locating your best estimate. But you could at least start having that conversation, which is very difficult to have at the moment, because the best estimate is a fairly subjective thing for a lot of these models. Because people put all their effort into building the models and not doing this sort of analysis for quite valid reasons. Yeah.
Another question, which is much more political question, really, and goes back to your very early slide where you were talking about the analogy between clinical trials and the climate. I mean, if you had an extremely life-threatening illness and there was only one of you, as
Yes.
is the case for most of us, there is only one of us. Actually, how closely do you, how good do you think that analogy really is? I mean, if I was sitting here as a pragmatic owner of a large simulation enterprise, I might be thinking, well, this is all well and good, but aren't we in a tearing hurry, etc. I mean,
I think there are. I mean, I think there are cases in clinical trials where certainly HIV drugs is one where people say, well, we should be actually prescribing these things before we do the clinical trials because they're saving people's lives. And certainly with the climate, we need to take action on climate. This isn't saying you shouldn't wait. I'm not saying that. But what I am saying is if you're going to do clinical trials, if we're going to do IPC type things, we should at least design them properly. I mean, a botched clinical trial is the worst thing, is the worst possible. Okay, where you wait for the clinical trial and then you find out it wasn't helpful.
Thank you, Peter.